Hello, I am Pablo Escobedo from University of Glasgow, and today I'm here to present our work entitled Printed Flexible Temperature Sensor with NFC Interface. My presentation is divided into four main parts. I will start with a short introduction to show the motivation and background of the developed work. Then I will look at the design and fabrication of the temperature sensor and the wireless NFC tag. Next, I will go to the results and discussion section, where I will show the outcomes of the work in different aspects: the sensor characterization, the electromagnetic performance of the antenna, and the results of the temperature sensing. Finally, I will outline the conclusions of the conducted work, without forgetting to acknowledge our funders, show the references used during this presentation, and also the contact information. Technological advances in smart sensors and wireless interfaces between the digital and the physical worlds are leading to the advent of interesting systems for remote sensing. Among various physical sensors, the temperature sensors have attracted much attention in healthcare and industrial applications. In fact, temperature is a crucial factor in determining, for instance, the shelf life of food products, since temperature alterations can provoke the growth or survival of food spoilage microorganisms and bacteria. The conventional temperature sensors are made of semiconductors, carbon derivatives, and temperature-sensitive materials. Conductive polymers have also attracted significant attention for temperature sensing, owing to their ease of processing and excellent electrical properties. On the other hand, among the different wireless technologies for the reading and transmission of sensor data, near-field communication technology, or NFC technology, provides a safe and convenient communication method for end users to check the quality of packed items simply by scanning smart labels with an NFC reader, which can be, for instance, an NFC-enabled smartphone. So, herein we present and we report the development of a printed temperature sensor integrated with a custom-designed NFC platform and a light emitting diode indicator to visually detect the temperature variations. So, let's turn our attention now to the design and fabrication of the system, starting with the temperature sensor itself. In this case, the sensor was fabricated using the conductive silver paste on a commercial PVC substrate. The figure below shows the schematic diagram of the sensor fabrication steps. Firstly, the PVC was cut into 2 by 2 cm pieces, and 2 electrodes were printed on the flexible substrate using silver paste. The samples were then dried in a hot air oven at 50 degrees for 30 minutes. A 2 mm gap was maintained in the middle of the 2 electrodes. Further, a 10 microliters of PEDOT PSS was dispensed in this 2 mm gap between the electrodes. Finally, the samples were dried at 50 degrees for 1 hour inside an air oven. The sensor was then integrated with the NFC antenna, as shown in the figure below, that is, in series with the LED indicator. This leads me to the next point, which is the NFC interface. The design tag antenna consists of a planar coil matched to the internal capacitor of the NFC transponder chip, which is in this case from Texas Instruments. The tag was designed to resonate at 13.56 MHz, which is the frequency compatible with NFC applications. With an adequate external electromagnetic field from a reader, this chip can provide a regulated output voltage of around 2 volts with an output current up to 500 microamperes. Considering the input capacitance of the NFC chip at the frequency of interest, which is 35 picofarads, the required inductance value was around 3.9 microhenries according to the resonance frequency of this parallel circuit. However, to reduce the antenna dimensions, a 1.8 microhenries inductor was designed, and then an external capacitor of 40 picofarads was placed in parallel to achieve resonance at the desired frequency. Let's now move to the next section, results and discussion. Firstly, we need to highlight that PEDOT PSS is sensitive to temperature. The rise in temperature increases the rate of carrier mobility in the material, and thus the resistance decreases. Therefore, the printed PEDOT PSS element was tested for temperature sensing. The sensor was characterized using a LabVIEW-enabled digital multimeter and a heating arrangement, that is, a hot plate having a digital display control as shown in the figure on the left. With this setup, the temperature was varied from 25 up to 90 degrees. The resistance was found to be decreasing with the increase in temperature, as illustrated in the figure on the right. Regarding the electromagnetic performance of the antenna, the left figure shows the experimental measurements of the inductance and quality factor of the PCB coil before attaching the chip. It can be seen that the inductance value at the frequency of interest is very close to the design value. Once the chip and the external capacitor were attached to the PCB, the resonant LC circuit was completed. Therefore, a new frequency characterization was carried out by measuring, in this case, the impedance and phase of the parallel resonant circuit. As observed in the figure on the right, the resonant frequency is very close to the 13.56 MHz desired working frequency. Further, the sensor was connected to the designed NFC antenna system. Figure shows the circuit and the system associated with the semi-quantitative temperature measuring setup. The setup consists of the custom-made NFC tag, the temperature sensor, and an NFC reader. In this case, the NFC tag was used to power the LED indicator, which was connected in series with the resistive temperature sensor. The temperature sensor is resistive, and thus its resistance decreases with the increase in the temperature value, as observed in the previous slide. Therefore, in the presence of the NFC reader, the LED glows with different intensities based on the resistance of the temperature sensor, as shown in the figure on the right. Currently, a rigid NFC tag is used, although we plan to extend this work further to develop a flexible version. The figure in the bottom left shows a schematic illustration of the sensing tag using a lux-meter mobile application, while the figure on the bottom right shows the intensity of the indicator at different temperature values. In particular, the intensity at 70 degrees was around 42 lux, whereas the intensity decreased down to around 14 lux at room temperature, that is 25 degrees. Finally, let me sum up the main points. This work presents a PEDOT PSS-based temperature sensor integrated with an NFC system. The temperature sensor was characterized using a digital multimeter for a temperature range from 25 degrees up to 90 degrees, and the sensor showed a 70% change in resistance for a temperature change of 60 degrees. In addition, the average degrees hysteresis of the sensor was found to be considerably low, below 3%. The sensing part was further integrated with an NFC antenna, and the temperature was obtained in a semi-quantitative way by means of the intensity of an LED connected with the antenna system. Therefore, this wireless-enabled temperature sensor can be used as a smart level in packaging application. Our aim is to extend this work to develop a fully flexible smart level for food packaging applications, for instance, for early spoilage detection. Before ending this presentation, we would like to acknowledge the NewCamp project supported by the European Union, and also here you can find the full reference list of the works cited during this presentation and the contact information. So that brings me to the end of my presentation. Thank you very much for your attention.